All right, we have one more set of indeterminate forms, and these are indeterminate powers, and they look like this. So if the limit as x approaches a of f of x raised to the g of x power, so we have a function to a function, produces one of the indeterminate forms, 0 over 0. 0 over 0? How about 0 to the 0 power? Infinity to the 0 power, or 1 to the infinity power, then try logarithmic differentiation. Okay, so often whenever we look at these, kids have a really hard time with these, as in understanding why these are indeterminate forms. You might think like 0 over 0 to the 0 power, why isn't that 1? Anything raised to the 0 power is supposed to be 1, so why aren't both of these things 1? Well, first of all, I'll explain the 0 to the 0 power. This is undefined anyway because you'd be dividing by 0. All right, this one here, we have a function. Both of these things are a function. One of them is approaching infinity, the other one's approaching 0, so it's not exactly to the 0 power. So that's why it doesn't give you a 1 as your final answer. And then likewise here, you might think that, hey, we have 1 times 1 times 1 times 1 times 1. Why isn't that equal to 1? But that's not what's happening. Once again, we have a function that's approaching 1, and we have a function that's approaching infinity. These are indeterminate forms, which means that they can approach absolutely anything. Logarithmic differentiation, remember what that means is that you take the log of both sides of something, then you take the derivative, and then you exponentiate back in order to fix it. And you do that so that you can get this function that's here in the exponent down to the bottom by a property of logarithms. Okay, so let's see this whole 0 over 0 and why that's equal to 1. I'm going to give you a little bit of an algebra lesson here. Let's say, for example, I have 5 to the third power over 5 to the third power, okay? So whenever I go to use my property of exponents here, I know that I'm supposed to subtract this. This is 5 to the 3 minus 3, which is 5 to the 0 power, which is equal to 1, right? Why is it equal to 1? Why is 5 raised to the 0 power equal to 1, or anything raised to the 0 power equal to 1? Because of division. So if I come back over here, this is a 5 times 5 times 5 over 5 times 5 times 5. Hey, what is 5 divided by 5? That's 1. What's 5 divided by 5? Also 1. 5 divided by 5 is also 1, and I get 1. Check. All right, so then you try to do the same thing with 0. You get 0 to the third power over 0 to the third power. You can see it doesn't work. And the reason why it doesn't work is because you just put a 0 down here in the bottom. This is the reason why you got something like a 0 to the 0 power. Doesn't make any sense. Berdoop, berdoop. Okay, it's an indeterminate form. Is it equal to 1? Or should it approach 1, I should say? Or it could approach, I don't know, maybe pi or something like that. Let's take a look at a particular example, this indeterminate form here. Ooh, I kind of recognize this limit. This looks familiar. It looks famous, actually. Taking the limit as x approaches infinity of 1 plus 1 over x raised to the x power. As always, just directly substitute stuff in here. So I've got 1 plus 1 over infinity is a 0 raised to the infinity power. I get 1 to the infinity power, which is not 1. It's indeterminate, but it is not L'Hopitalable. So what you do is this. You're going to, you need to use L'Hopital's rule, which is associated with derivatives, and we're going to take the derivative by using logarithmic differentiation. So my suggestion here is to make this equal to some generic variable like y, and make this as some sort of equation. It's equal to the limit as x approaches infinity of 1 plus 1 over x to the x power. And now let's take the natural log of both sides. So I'm going to take the natural log of y is equal to the natural log of this whole thing. You know what I'm going to do? I'm just going to copy and paste this thing. Let's duplicate. Whoop, boop. Right there. Okay, with a property of limits here, this natural log can pass through this limit, and then I'm taking the limit of the function that's inside of here. Right, so this is equal to the limit as x approaches infinity of the natural log of 1 plus 1 over x raised to the x power, and now we have a power to a power. So this x guy gets to come down. So we're going to bring that thing down, limit as x goes to infinity of x times the natural log of 1 plus 1 over x. Now realize that this natural log of y is still around, and we'll have to deal with that guy at the end of this particular problem. Okay, so now when I do my direct substitution here, I get infinity for your x, and then times the natural log of, I'm going to have a 1 inside here, right? Because this is 1 over infinity. This is 0. I'm taking the natural log of 1. Natural log of 1 is a 0. And now that's our indeterminate product. And I fix an indeterminate product by turning it into a quotient. I need to put one of these functions down in the bottom. Do I want to put the x down in the bottom, or do I want to put this ugly thing in the bottom? Of course, I want to put the x down here in the bottom. So I'm going to rewrite this as the limit as x goes to infinity, the natural log of 1 plus 1 over x over 1 over x. And now, whenever I plug in my infinity, I'm going to get the indeterminate form of 0. We already talked about that one being a 0. And then on the bottom, I have 1 over infinity, which is another 0, which is now a check for L'Hopital's rule. So I'm just going to take the derivatives of the top and the bottom here. So the limit as x goes to infinity of, and I'll have to use the quotient rule, or just think of this as u prime over u. So I want to make some sort of fraction. I know that the bottom is going to stay the same, and now I want to take the derivative of this interior to go on the top. Right, and this is just the top of the fraction. I still have to take the derivative of the 1 over x to put it on the bottom. Okay, all right, so the derivative of 1 plus 1 over x is just, well, the 1's going to disappear, and on this part is going to be 1 over x squared, but negative, right? Because we've seen this already 13 times in this lesson. That's right, count it, go back, look at all the videos, it's 13. So x to the negative 1, taking its derivative is negative x to the negative 2 power. Okay, again, that's just the top. Now I'm going to do the same thing on the bottom. Well, we just took the derivative of 1 over x. It's negative 1 over x squared. Got a complex fraction. Let's fix that complex fraction, shall we? And I can fix this complex fraction by just multiplying by the fancy one in this particular case. In this particular case, I'm going to multiply it by this fancy one, negative x squared. Negative x squared. Top and the bottom. Why did I do that? I did that because this will cancel with that, and then this will cancel with that. Super easy. Equals the limit. Oh, I'm running out of paper. I'm just going to have 1 over 1 plus 1 over x. Okay, let's plug in our infinity now. All right, so the 1 stays up top, and on the bottom, I'm going to have 1 plus 1 over infinity is 0. I just get 1. Is the value of this limit 1? We had, what did we have our indeterminate form? We had our indeterminate form is 1 raised to infinity. I just said that that's not always equal to 1. We just got 1. Well, we're not done with this one. Remember that that is equal to, if I come back over here, it's actually equal to the natural log of y. In other words, the natural log of our limit is equal to 1. So the natural log of y is equal to 1. I need to exponentiate this to actually get the value of our limit. So I take the the e to the power of the natural log of y on the left-hand side and e to the first power on the other side. And I get, on the left-hand side, they cancel out, just giving me y, which is the value of our limit, which is, remember, the limit as x approaches infinity, 1 plus, 1 over x to the x power, right? Remember, that's what I said right up there, is equal to e to the first power. There you go. That is the limit definition of E. And so we've used it. You used it in, what was that class called? Algebra 2. We talked about it in this class. Maybe you saw it in a calculus, pre-calculus, I should say. And now we have the tools, or we developed the tools in order to prove that this limit with the indeterminate form 1 to the infinite power is equal to e. And you can see here's a case where we have this indeterminate form, 1 to the infinity is not equal to 1. Why is that? Because this is a function and this is a function. This function here is approaching 1. This function here is approaching infinity. They're in a tug of war, and there was a compromise, and the compromise to this one was equal to e.